Hi and welcome. I'm trying to learn particle physics. Today, matter, antimatter imbalance. And after we've done it, we're going to do standing yoga. And if you participate in the standing yoga, then it's at your own risk. And this is part 3-4 of matter-antimatter imbalance. Theorists later found that CP violation among, this is a bit earlier, that CP violation among counts could be explained if three heavier unknown particles were disrupting them. All three of these particles have since been found. The bottom charm and top quarks and their presence, along with CP violation, is now a mainstay of the standard model. So it's about that there is more of one than of the other one. And one was with the counts, where was something wrong, but three particles were found which explain this matter-antimatter imbalance for the counts. Those particles also provide new sources of CP violation. In the intervening half-century, we have measured all the main predicted sources with Large Hadron Collider beauty, measuring the last among charm quarks just last year. Now the whole thing looks completely understood and all is well, says Gersabek. Okay, we found more particles and they had explained why there was matter-antimatter imbalance. But there is just one tensy problem. Patterns in the cosmic microwave background. The leftover radiation from the Big Bang, combined with calculations of the number of galaxies that must exist, tells us the early matter-antimatter imbalance we need to explain today's matter domination. It's tiny. About 1 part in a billion is there more matter than antimatter. But the CP violation we have found so far doesn't account even for a billionth of that. There's still a little difference, even if you account all the other particles, between matter and antimatter. Perhaps there are unknown sources of CP violation. In 2017, Large Hadron Collider beauty saw an unexpected hint of the effect among heavier versions of protons and neutrons. If the elusive particles known as neutrinos are their own antiparticles, that would also allow extremely rare processes to supply an extra source of asymmetry. There is some thinking about that some things are themselves their own antimatter, for the neutrinos, for example. But to expect such small, unconfirmed effects to account for the current huge mismatch seems like wishful thinking. Now they said something about 1 billion, if it's another place they said something about 1/3, that there is 2/3 matter to 1/3 of antimatter. I don't know where we're now talking about. Here the antimatter problem meets a wider fallacy in fundamental physics. At the moment, we're at quite a curious place, because we found all the particles of a standard model and it looks like the standard model can explain everything, including CP violation. Now having the standard model with the 20, 25 or whatever particles on it, and if someone looks at it, it looks as if every particle has been found which exists. The standard model was made some time ago and all these elements predicted were found, I think, already. And so basically the idea is, these are all the particles which exist. Now, these particles together should explain all the universe. But it does not. But at the same time, we know it's not right, and there's other stuff out there. Gersabek says that. Stuff like dark matter, for example. The mysterious entity that makes up most of the gravitating matter in the universe. The Large Hadron Collider at CERN was partly conceived to make heavy, dark matter particles in its high-energy collisions. Okay, we're making collisions and we're trying to produce heavy dark matter to explain things. But it has found diddly squat, besides the Higgs boson, the mass-giving particle discovered in 2012. Diddly squat. I think we mean nothing of worth. The hope is, once the machine is up and running again in 2022, Precise measurements of rare processes that Large Hadron Collider building specializes in will offer a chance to solve the antimatter and dark matter problems, not by manufacturing new particles, but by measuring their ghostly influence on already known ones. They saying basically, they probably will not be able to create these heavy dark matter particles, but they might be able to measure what these heavy dark matter particles are doing to other particles. They are able to measure the effects of them. This is the physics equivalent of reaching up a hand to have a rummage around on a shelf you can't actually see. With some of these measurements, we can access mass scales for hypothetical particles 2 or 3 orders of magnitude beyond the reach of the Large Hadron Collider for producing them directly. What was it? With some of these measurements, so the Large Hadron Collider, we can access mass scales for hypothetical particles 2 or 3 orders of magnitude beyond the reach of the Large Hadron Collider for producing them directly. They say they can produce with the Large Hadron Collider just some particles, but they can get 2-3 times the more likelihood or something of measuring the effects which these have. So basically saying it's way easier to measure the effect of something when to find out directly what is happening with the effect. It's a very, very powerful search tool to cover a huge lot of ground, says Gerwig. The hope is that these heavier particles could be sources of CP violation, in effect repeating the trick that solved the Cowan problem. I haven't really understood what CP violation is. A phenomenon called CP symmetry gives hint of a plausible alternative. The idea is that since matter and antimatter are just mirror versions of one another, for each type of particle there is an antiparticle with an opposite charge, and this is C symmetry and parity, or P symmetry. Put together, these make CP symmetry. I don't understand what I say there. CP symmetry, I think they mean that is for every particle another one with the opposite charge. I think that is it. There are protons and there are electrons and there are positrons. There are protons and negative strons, whatever. Something like that. But if they say, I don't know what it was here. Electron, positron. Proton, antiproton. But there is no guarantee. So basically, the guarantee to find the effects of heavy dark matter particles, which would explain why there is more matter than antimatter. We've got a few hints here or there of things that might be going on, but nothing firm, says Gerwig. A few kilometers due west of Large Hadron Collider Beauty, some physicists, including Mel Brunot, are betting on a different approach. Okay, there's some people in Switzerland at the Large Hadron Collider working, and some other people are a few kilometers away working. Rather than searching for new physics at very high energies, says Jeffrey Hongst, at CERN's Alpha experiment. Okay, somewhere at CERN are also people working. Maybe it's the same place. Whatever, there's two groups working on something. And there's someone says of the other group, we decide to look really carefully at things we think we understand and see if maybe we've overlooked something. So the one thing we are looking, what can we find new? Can we find the effects of something which is there? Can we find the things which have as an effect? And the other one saying, let's look over all what we already have if we made a mistake or overlooked something. Overlooked something, no mistake, overlooked something. A mistake to overlook something. The mistake was to overlook something. The aim of the experiments at the so-called antimatter factory is to solve the antimatter mystery by making large quantities of whole anti-atoms. are we basically saying we have more matter than antimatter, so let's produce antimatter until we have it even. All the differences between matter and antimatter come about because they have opposite charges. So the idea is to cancel those differences by taking oppositely charged antimatter particles and making neutral atoms out of them. They have the electrons, and there exists the antimatter particle, the positron. We're taking the positron, which is positive, but it is an electron, and we're making it neutral. An atom of anti-hydrogen, the simplest imaginable anti-atom, should work exactly like a conventional hydrogen atom. I don't really get it. Hydrogen, that's the first element, and helium is the second. Hydrogen has now one proton. And how many electrons? And what would be no anti-hydrogen? Whatever. If it doesn't, so if a neutral anti-hydrogen is not the same as a hydrogen, then nature's most profound symmetry is broken. CPT symmetry. This adds time reversal or T symmetry to the CP mix. If particles swap charges and their orientation in both space and time. I think they mean at one place and another place they are just saying, I'm taking it down to the most simplest form. Maybe that is all. It's just here particle and here particle that they are changing. Now they're saying maybe someone changes just next year. If particles swap charges and their orientation in both space and time, if the universe is completely mirrored, then the laws of physics should work the same way. This assumption lies at the heart of relativity and the quantum field theories underlying the Standard Model. If we find any difference that would have dramatic impacts on physics, okay, we're saying we're creating a lot of neutral antimatter things, and they should work the same as the original matter things. So there's matter, that is a normal hydrogen thing, and there's antimatter, the anti-hydrogen, I think, or something like that. And they're saying, how about we're creating a neutral anti-hydrogen, which is technically now not antimatter because it is not it has not the opposite charge as the normal hydrogen. And it must be the same, because it is no longer the antimatter particle to the normal matter particle hydrogen. It has the same charge, or the neutral charge. Maybe one has a neutral charge related to hydrogen. If it does not, then something would be wrong. The problem is working with antiparticles with their penchant, I don't know the word, for going up in smoke. They mean, if they have antiparticles, they can keep them long. They're running away or they're pinching or getting to smoke. To stand a charge, the antimatter factory is doing the opposite of what CERN is famous for, slowing particles down. A dedicated machine, the antiproton decelerator, is fed antiprotons and calms them so they can begin to create stable unions of positrons and to form stable antihydrogen atoms. I don't know where the difference between antiprotons and positrons. Antiprotons and positrons. Antiprotons are the opposite of protons, and positrons are the opposite of electrons. They are saying they exist to shortly these electrons. So we're saying, hey, let's have them longer, not just for thousands of seconds, but let's have them for 1 to 2 seconds. By slowing them down, we let the particles be slowly. And now by having them slowly, we hope that now these opposite ones of protons, the antiprotons, together with the opposite one of the electrons, or protons, electrons, the opposite one of the electrons, the positrons, are starting to go together and make new element, starting to react with each other. And that would then form antihydrogen atoms. Now, that was the particle physics part. If you were here for particle physics, you go directly to the next part of particle physics. If you stay and participate in the 10-second yoga, then it's on this. So we will fit them together and we're breathing in and lifting it up. And breathe out the arms down. In the arms up. And out and down. Breathe in the arms up. Bring the hands to touch and lower the hands down towards it. Now we've had gone way over time. We don't have time left for a singular. I thank you very much and until next time.